So the things that make those speeds bigger and smaller, faster and slower, are important questions to consider when you're a chemist. And so here are just kind of an overview of what happens. Small molecules tend to react a lot faster than large molecules. Small molecules, you can usually just use them as is, but larger molecules, sometimes there will be a target zone, and getting the right chemicals in the target zone can take a little bit longer, so that's kind of a general trend. Gases tend to react faster than liquids in general, and liquids tend to react faster than solids. Again, this is general, but it has to do with orienting things. Ions generally react faster with molecules. If you have more surface area, you can have a better chance and faster reaction than if it's like a concentrated source. I'll show you a cool video of this here in a little bit. If you have higher concentrations of reactants, that means you'll have higher collisions and faster reaction rates that way too. Generally speaking, temperatures will make particles collide faster. It also gives them greater kinetic energy, so that makes it faster. And catalysts are substances that can make a reaction go faster without being used up themselves. And that's pretty cool. We'll talk about catalysts more here in a little bit. But if you have a catalyst, it should make your reaction go a lot faster, which is neat too.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
Both of those test tubes have hydrochloric acid, but in one test tube, the concentration of HCl was 6.0 moles per liter, and that's a lot bigger than 0.3 moles per liter. And you can see how the magnesium metal just reacted super fast with a 6 molar HCl and very slow with a 0.3 molar HCl. So on the right-hand side there are two graphs corresponding to the different HCl concentrations. And the HCl graph with 6 molar concentration, which is on the bottom there, you can see it's almost a straight up and down line. It's very, very fast reaction. The whole reaction was done, say, in less than 50 seconds. On the other hand, the 0.3 molar HCl, you can see it took closer to 400 seconds to get to approximately 0 magnesium. So the amount of the concentration does make a big difference. The bigger the concentration value, the faster the reaction in general, which is kind of a cool thing.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Solids, as we saw in the intermolecular forces chapter, are very dense. The atoms are very close to each other. And when you have a solid, then you only have the outermost level of the solid exposed to whatever reactants there are. So, for example, there you tried to use a Bunsen burner on solid lycopodium powder, which is some kind of powder from mushrooms, apparently. Anyway, it doesn't hardly react at all. But if you spray the lycopodium powder through the Bunsen burner, man, it's like they use this for magic tricks, apparently. Sometimes it's very kind of flames and stuff like that. Those little particles of lycopodium react a lot faster than the bulk is, because the bulk only affects the outside. Also, in this set of pictures there, you can see two effects of iron. On the left-hand side is an iron nail in O2, and it does react, but it's very slow. On the other hand, steel wool, which is essentially iron, but very, very low density, it reacts super fast and will burst into flames when you have it in pure oxygen. So again, the amount of surface area can make a big difference in terms of the speed of the reaction.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
In a different chapter, we use this video to talk about stoichiometry, how to figure out amounts of products being created, stuff like that. We'll come back to this here again because this is a great example of a catalyzed reaction. Hydrogen peroxide, H2O2, does break down to water and O2. So if you buy it in the store, it's in a brown bottle. You're supposed to keep it out of the sunlight in a refrigerator to keep it from breaking down. In the presence of a catalyst like manganese 4 oxide, MnO2, not manganese dioxide, but anyway, the MnO2 then makes the H2O2 decompose very, very fast, as you could tell. It's so fast that it's amazing, really, and it breaks down to H2O and O2 right away. And this is an example of what's really called a positive catalyst, which is what most catalysts are. It makes a reaction go a lot faster than it would be without a catalyst, and that's most of the time what catalysts are for. However, you should know that there is a term called a negative catalyst. A negative catalyst, although not as common, do slow a reaction down. And sometimes that's important too. If you want a reaction to go slower, a negative catalyst will make that go slower. All catalysts, whether they're positive or negative though, catalysts will be used up in the reaction and they'll be regenerated at the end. So as an example, in the H2O2 example, you can see the water on the bottom is kind of murky. That darkness is from the MnO2. And if you took the water and MnO2 and you dried it really well, you could reuse that MnO2 in another set of reactions. Catalysts, in theory, just keep going and going and going on and on and on. They usually have some kind of final point where they no longer work because of some weird chemical pathway, but they can go on for many, many transformations, which makes them very powerful.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
Warmer temperatures make reactions go faster, and we'll talk about why that's the case in a little bit in this chapter. But if you need a reaction go faster, you can warm it up, and that will certainly make it go a lot less, as you could see from that food dye example. A chemist's rule of thumb for a reaction is that by increasing a reaction temperature by 10 degrees should basically double the speed of the reaction. So as an example of that, let's say you did a reaction at 20 degrees Celsius and it took 5 minutes. Well, if you then did the same reaction at 30 degrees, roughly 10 degrees higher, it would take half that time, or 2.5 minutes. So that can be kind of useful. That's not totally followed all the time, but it's a rough guide and stuff, especially if you have a reaction where timing is critical.